This is the pre-lab video for experiment 10, the sodium borohydride reduction of vanillin. This is vanillin. We're going to react it with sodium borohydride to produce vanillyl alcohol. Notice there is a question mark above the reaction arrow. That's because the goal of this experiment is to actually develop a method for doing the reduction. What chemicals should we use? How much should we use? What should the reaction conditions be? Temperature, time, etc. If you read the lab manual, it does not give specific directions on how to conduct this experiment. So that's what we're going to do today. We're going to develop a method for reducing vanillin to vanillyl alcohol. This is a list of the 10 steps in conducting an organic chemistry experiment that we've been following for the whole semester. Underneath each heading are listed the specific things that we learned this semester. So if we want to design a method to reduce vanillin to vanillyl alcohol, we're going to go through this methodology. The first thing we'll do is we'll go do a literature search. We're going to see what other people have done. What was their synthetic scheme? Were there any side reactions that they noted? What sort of techniques did they use? At that point, we're going to go and we're going to assemble our glassware and instrumentation. So we'll have to make sure we have all of that in our labs here at UAA. Reagent options also, we'll look for the reagents that we'll need in the chemical stockroom and what sort of solvents we're going to run the chemical reaction in. As always, we're always going to consider safety as our #1 priority, so we'll review the SDSs for all the chemicals that we're going to use, determining the hazards, our personal protective equipment, any physical properties that we might need to consider when undertaking our chemical reaction. We also need to decide what sort of scale we're going to run our reaction on. Should we do it on the micro scale or a larger scale? And one thing that we always like to do is determine if there are any safe chemical alternatives to the chemicals that we've chosen, and are there any green alternatives to the chemicals, because we do need to dispose of every chemical that we use and do it safely. So here's where our actual chemical reactions start. We need to determine the temperature, the time. Do we need to stir it? Do we need to shake it? Are we going to reflux? What order are we going to add our chemical reagents in? And do we need any special catalysts? A variety of things that we need to consider for our chemical reaction. After we've performed that chemical reaction, the synthesis part, we need to work up our product. Do we need to extract our organic material from aqueous, washings, neutralizations? Typically, if we do have a solid, we're going to do some filtrations. Should we consider distillations, centrifuge, drying, and evaporation? After we've done that workup, do we need to purify our material? Do we use recrystallization, chromatography? Would we wash it again? Or could we try trituration? After purification, we need to do some analysis to identify our material that we've produced and see if there are any side products. We can do melting point, infrared, NMR, GC, UV visible, and thin layer chromatography. Those are the techniques that we learned this semester. And we're always going to do calculations at the end. Percent yield to see how successful we were in converting our vanillin to vanillyl alcohol. Percent composition, percent recovery, and RF values. Those will not be used for this experiment. And then document our results in our lab notebook, and that's what I will be doing. Any observations that I see, any data we take, any plots or graphs will be put in the data notebook. And then finally, we're going to formulate some conclusions before writing our report, do some yield analysis, maybe some error analysis, and method analysis. Is the method that we came up with sufficient, or do we need to modify it to improve our yield or make our product purer? And finally, on your part, your homework assignment is to write a lab report and turn it in as the last assignment for the semester. As part of our planning and preparation, I did a literature search. I went and I found 7 articles on the internet that had used sodium borohydride to reduce vanillin to vanilla alcohol. The reaction mechanisms are that I'm going to have it in a basic solution, which will deprotonate the phenol part of the molecule. Then my sodium borohydride, the hydride anion, will attack my carbonyl carbon, leaving me with the dianion. Working that up with a little bit of hydrochloric acid, I can reprotonate both of those oxygen anions to form vanillyl alcohol. The hydrochloric acid also has a secondary purpose. We're going to add our sodium borohydride in excess to push the reaction toward completion, and we need to neutralize that, and HCl will do that, reacting with the hydride anion to form hydrogen and chloride anion. It will also react with any excess base that's in our solution to form water and chloride anion again, and the Cl- would be soluble in the aqueous part of our reaction mixture. As part of our planning and preparation, I have decided to use a round bottom flask with stirring, and here's the apparatus I've come up with for this reaction. I'm going to attach to that an additional funnel to add my sodium borohydride and to add my HCl. After the reaction is complete, we'll set up a vacuum filtration apparatus in the hood and we'll separate the solid from the liquid. The reagents that we're going to need are vanillin, sodium hydroxide, HCl, and sodium borohydride, and I've determined that I can obtain those from the chemical stockroom. And we're also going to need some ethanol as a solvent for the reaction, and I can get that also in the chemical stockroom. I went to the library and looked up the SDSs for the 6 different chemical reagents that we will be using in this experiment. Hydrochloric acid is corrosive, so is sodium hydroxide, and they can both cause chemical burns if they get on your skin, so we will be wearing gloves during this experiment. Sodium borohydride is also caustic, and it will decompose violently with acid. So, as part of this reaction, we're going to add our sodium borohydride drop by drop to control the reaction rate, and we're also going to chill the reaction in an ice bath to make sure that it is at a constant controlled rate of reaction. Sodium borohydride is also sensitive to air, so we need to make sure we have limited exposure time of that reagent to the air. Again, we're going to wear lab goggles, we're going to wear our gloves, and we're going to work in the hood. I've decided that we'll do this scale on the millimole scale, so we're going to be using 10 millimoles of each of our starting material. I also looked up in the literature some alternatives to sodium borohydride. Lithium aluminum hydride is a very commonly used reducing agent. However, it's even more reactive. So special precautions need to be taken that we don't have here at UAA. A second green alternative would have been polymethyl hydroxyloxane as the reducing material, and that one looked promising until I went to look for it in the stockroom, and that one was not available either. So we're going to go with sodium borohydride. The third step in our process list is to actually do the chemical reaction. We're going to start off by doing the sodium borohydride reduction. We're going to assemble our glassware in the hood. I'm going to weigh out 10 millimoles of vanillin and place it into our 25 milliliter round bottom flask. To that, I'm going to add 5 milliliters of ethanol, and I'm going to stir that to dissolve it. And then I'll put the whole 25 milliliter round bottom in an ice bath. In a separate vessel, I'm going to dissolve 10 millimoles of sodium borohydride, noting that that is 4 times excess in a molar ratio because there are 4 hydride ions here. And I'm going to dissolve that in 10 milliliters of 1 molar sodium hydroxide. I'll place that in my addition funnel, and then I'll start to add it dropwise to the round bottom flask, monitoring the temperature at the time to make sure that my reaction is not too exothermic. Once I've added all of the sodium borohydride, I'm going to remove the reaction vessel from the ice bath, and I'm going to stir it for an additional 30 minutes to allow time and temperature for the reaction to occur completely. The next step in our reaction is to actually add our HCl to reprotonate these two oxygens to react with the excess hydride and to react with any excess base that we have. I'm going to remove our vinyl alcohol contents from the round bottom flask and transfer them over to a 100 milliliter beaker where it will be easier to add the HCl. We'll chill that beaker in an ice bath to also control its rate, and then we will add the 3 molar HCl dropwise until the pH is reduced to less than 6. We will test that periodically with pH paper, and also we should see any H2 gas that's evolved stop, because once we've reacted with all our hydride, there should be no more H2 gas being evolved. Then we'll chill that again until the crystals have formed, till our vinyl alcohol is precipitated out of that new aqueous solution. We'll then collect those crystals by vacuum filtration. We'll wash it several times with ice water, and then we'll dry it to a constant mass in a 90°C oven. Unless we think we need to purify it, and then we'll wait on this drying step. If we do deem that we need to purify it, we can recrystallize it from hot ethanol. Several of the literature sources that I read had used hot ethanol and had good recovery. We'll collect those crystals by vacuum filtration, wash it 2 times with ice water, and then dry it to a constant mass in a 90°C oven. For our analysis and metrology step, we're going to perform IR spectroscopy. The spectrum for vanillin, which is an aldehyde, and vinyl alcohol, which is an alcohol, should have completely different IR spectrum, and we'll also perform NMR on our final product. Our calculations, we're going to do percent yield. What I've outlined here is actually a detailed step list on how to calculate percent yield. The scenario that we have here is that I start out with 1.5153 grams of vanillin. I react that with 0.4375 grams of sodium borohydride, and then after vacuum filtration and drying, I have 0.6038 grams of vinyl alcohol that I've isolated. In order to calculate percent yield, the first thing we need to do stepwise is to write the balanced equation for the reaction. 4 moles of vanillin reacts with 1 mole of sodium borohydride and 4 moles of water to give me 4 moles of vinyl alcohol, some borate, and some sodium hydroxide. Our conclusions from that equation is that 1 mole of sodium borohydride reacts with 4 moles of vanillin to form 4 moles of vinyl alcohol. So now, based on that equation and how much material I've used, I need to calculate which one of my starting materials is actually my limiting reagent. To do that, I'm going to calculate how many moles of vanillin and sodium borohydride I used. So I take the mass of the vanillin, divide by its molecular weight, and calculate the number of moles of vanillin. I get 0.009956 moles. I take the mass of my sodium borohydride, divide by its molecular weight, but I also multiply by this factor here to account for the fact that my sodium borohydride has 4 hydride atoms on it that can react. So I have 4 moles of hydride for every 1 mole of sodium borohydride. And so I have 0.04625 moles of hydride. And if I look at that, 0.009956 is less than 0.04626, so vanillin is the limiting reagent. From that information, we can then calculate our theoretical yield. I take my vanillin, because it's the limiting reagent. I convert it from grams to moles of vanillin. I take my moles of vanillin, convert it to moles of vinyl alcohol. I take my moles of vinyl alcohol, convert it to grams of vinyl alcohol, and that would be my theoretical yield, 1.5352 grams vinyl alcohol. And finally, to calculate percent yield, that's just my actual yield, which would be my 0.6038 grams divided by my theoretical yield, which is 1.5352 grams, and multiply that times 100, so I get 39.33% yield. Number 8 on our list is to document our results. I will be keeping a lab notebook where I document any data that we take and any observations that we have during the experiment. I will include these in the video of the lab experiment. Number 9 on our list is to formulate conclusions. We're going to identify any sources of yield loss. Materials transfer is common in organic chemistry experiments, transferring from the round bottom flask to the beaker, to the Buchner funnel, to the watch glass. The reaction itself might not have been complete. Did we heat the reaction long enough? Did we have a high enough temperature? Was the reaction in equilibrium? There also could have been side reactions. We might be able to tell that from our infrared spectra or our NMR. If not, we might want to perform some other type of analysis like GC or liquid chromatography. When we crystallize our material out, the material might have been soluble in our ice water and we could lose some material there. And also in our vacuum filtration system, inevitably, some material passes through the filter paper. So on our conclusions, one thing we're going to think about is method analysis. Do we need to allow longer time for the product to react? Do we need a higher temperature? And should we recrystallize the product? Do we need to purify it? And number 10 on our list is to actually share our information in the form of a report so other people can see what we did. You're going to do this in the form of a homework assignment. I'd like you to calculate the percent yield from this experiment. I'd like you to analyze the IR spectra for vanillin. I want you to do this by drawing the molecule directly on the spectra and draw lines from the functional groups to the corresponding signals. And do that for the signals that are all greater than 1600 reciprocal centimeters. The third item is I'd like you to explain why the carbonyl signal is less than 1700 reciprocal centimeters. You might have to go to the literature to find that out. I'd also like you to analyze the IR spectrum for our product, vinyl alcohol. Again, draw the molecule directly on the spectra and draw lines from the important functional groups to their corresponding signals. Do that again for signals greater than 1600 reciprocal centimeters. And then taking those two spectra together, explain how these IR spectra indicate that vanillin has been converted over to vinyl alcohol. I'd also like you to analyze the vinyl alcohol NMR spectrum, draw the molecule directly on the spectra, and draw lines from the protons on that molecule to the corresponding signal on the NMR. Okay. And G, I want you to calculate the percent of vanillin, that's our starting material, in the product. You can do this by using the integration of the signal near 9.79 parts per million. That's the signal due to the aldehyde proton on our starting material. And then finally, explain why the acetone signal in the NMR shows up as a quintet. Again, you might have to go to the literature and find that out. I have included one article on the Blackboard to help you do this. And that's it.